Welcome back to my channel Mahendra Yami NIT. Today I am going to cover the topic additive manufacturing. These are the parts which is made by using additive manufacturing. These are the turbine blades and very complex figure which is made by using additive manufacturing. This is the human finger, human legs which is made by using additive manufacturing. These are some parts of engines and bicycle uh, which is manufactured by using the additive manufacturing. Some bearing system, some engine part, crankshaft, gear, which is manufactured by using additive manufacturing. This is the definition of additive manufacturing. Additive manufacturing refers to a process by which digital 3D design data is used to build up a component in layer by depositing material. In additive manufacturing is just reverse of subtractive manufacturing. In subtractive conventional manufacturing, what happen? We remove the material in the form of chip. In additive manufacturing, what happen? We add the material in the form of layer by layer and create the our 3D product. It is also known as 3D printing. What you see is what you build. That is the more concise definition of this additive manufacturing process. Whatever you are seeing in the real world, you can build. Difference between rapid prototyping and additive manufacturing. Additive manufacturing is mainly used for rapid prototyping because in initial conventional process what happened, we have to do lots of trial run on the model by reducing the dimensions, and then in lots of time and fund is wasted in during the testing of the product which we want to make. So here in additive manufacturing we have to provide the design and put the material and property what we need. Then this is a process which is a very rapid prototyping. Here prototyping is a very rapid. It is not used for bulk production, mass production, but for rapid prototyping, this is mainly used additive manufacturing. Additive versus subtractive manufacturing. First thing is the part complexity. If complex part is there, we cannot manufacture by using subtractive manufacturing. Then we use additive manufacturing for creating that type of part. Material, lots of material is there, like polymer, metal matrix and ceramic matrix, which cannot be machined by the conventional process, but by using additive manufacturing we can fabricate the component by using that material. Speed, the manufacturing speed, in how many less time you can produce the component. In subtractive manufacturing you have to make the fixture, you have to arrange the tool and fix the workpiece. Suppose you are working on CNC lathe or conventional lathe, so lots of issues there. But in additive manufacturing, just we we print the material like it is 3D printing machine. So we print the material in the desired form. You don't need to cut the pieces. First you make by using casting process, then after that you do the machining and cut different parts and the dimensions whatever slot is required. Part quantity, here you quantity is also you can high quantity. In bulk mass production you can do. Cost is also low, but polymer printing is less costly, but metal printing machine is having high cost in crore if you going for purchase that type of 3D printing machine. Additive versus substrate manufacturing. Here this is a cup, the feature that represent problem using CNC machine. So the cavity here may be too deep to machine. The undercut here cannot be performed without more than 3 without more than 3 axis machine. So here if you want to make this contour undercut, then you have to use the 3 axis machining. Bases cannot be machined in machining must hold using a fixture. Sharp internal features cannot be machined without a tool radius. So these are the problems which arises in the subtractive manufacturing. Then we move towards the additive manufacturing. These are the features that represent problem using CNC machining. This data is taken from the source is Gibson Additive Manufacturing. Generic additive manufacturing. What are the steps in during the fabrication of that cup? First, you have to make the CAD computer aided design of the cup. Then that file will be converted into STL file. Then this file transfer to the machine on the 3D printing. Then process building will happen. Machine setup, next building. Then we remove the material. After that, post processing will happen. Then eighth one is the application. We can use this cup for drinking the tea. So that's are the steps during the additive manufacturing process. In in last slide, you have seen the problems during the CNC machining. In this, the steps. What are the steps in additive manufacturing process? CAD model into STL format. How we convert the CAD model into STL format? STL uses triangle to describe the surface to be built. Each triangle is described as 3 point and a facet normal vector indicating the outward side of the triangle in a manner similar to the following. So these are the missing. This is the CAD model. Suppose you are working in NC software, FC software. Then in that all the software, what happened? First you have to make the design on which you want to do the analysis. After that, you have to provide the property of the material. What are the property of the material? Then you have to provide the boundary condition, which end is fixed, which end is having the load, and this step is the meshing. What happened in meshing? We we discretize the whole model into a small element. So here triangle is the smallest triangle. Here lots of triangle you are showing. So this is the thing happen in triangle vertices, end loop, end facet. So these are the also source Gibson taken from the Gibson additive manufacturing. Effect of building using different layer thickness. If the layer thickness is high, if you are putting the thickness of layer is high, then there will be the effect on the product. So there are the three products which is manufactured by a different layer thickness. Other related technology which is used in additive manufacturing, like the additive manufacturing, reverse engineering technology. What happen in reverse engineering? Suppose the product is given, you want to make the missile tank, and you have the tank. From the tank, you have to study all the things, why, how it is running, what are the concept, what are the mechanism of the machine, how it, mm, so all the things you have to learn by seeing the product. So from the product, you have to come to the initial stage, how it can be manufactured. So this is the reverse engineering technology. Computer aided engineering by using computer. This is a computer aided engineering. So 3D CAD model plus engineering analysis software package, haptic based CAD. So these are the other technology which is also taken from the Gibson additive manufacturing. Difference between various additive manufacturing technique. Lots of additive manufacturing technique is there. By using laser, by using electron beam, by using wire arc. So what are the characteristics on that basis the lots of the technique is used in additive manufacturing. Techniques used for creating layer, technique of bonding the layer together, speed, layer thickness, range of material, accuracy, cost. So these are the parameters which decided which process you will use for doing the layer by layer deposition and solidification. What property you need? These are the things. You have to do lots of the research on this area. Evaluation. What are the history behind the development of additive manufacturing process? This timeline lays out past, present, and potential future additive manufacturing development and application. Courtesy of Graham Tromans, 1988-1994 is the year in which rapid prototyping came into the picture. In 1994, rapid casting. In 1995, rapid tooling. In 2001, additive manufacturing for automotive. In 2004, aerospace polymer. In 2005, medical polymer jigs and guides. 2009 medical implant metal, in 2011 aerospace metal, in 2013 to 2016 nano manufacturing, in 2013 to 2017 architecture, in 2013 from 2013 to 2018 biomedical implant, 2013 to 2022 in situ biomanufacturing, 2013 to 2032 full body organs. These are the history behind the development of component manufactured by using the additive manufacturing technology. The automotive and aerospace industry are the two of the main beneficiary of additive manufacturing. In 2012, GE Aviation bought AM Morris Technologies, one of the biggest metal additive manufacturers in the world. GE is ramping up AM manufacturing of aero engine fuel nozzle. The conventional method of making fuel nozzle requires making 20 separate parts and welding them together, which is extremely labor intensive and has a high scrap rate, said Graham Thompson, Principal and President of AM Consultancy GP Thompson Associate. AM allows the creation of pre-assembled nozzle. GE predicts that by late 2015-16 it will make 10 to 20 fuel nozzle for each engine using additive manufacturing. The company also envisages that 50% of a jet engine will be additive manufactured within current lifetime. This source is taken from the Royal Academy of Engineering. This is also the figure which is also taken from the Royal Academy of Engineering. Rapid prototyping, rapid casting, rapid tooling, additive manufacturing for automotive, aerospace, polymer, medical, polymer, jigs and guides, medical implants, aerospace, metal, nano manufacturing, architecture, biomedical implant, in situ biomanufacturing, full body organs. So these are the graph current and potential industries for additive manufacturing. Source is taken from Google Image, aerospace industry, dental industry, jewelry, automotive, implant, surgical devices, textile, furniture, prosthetics, specialty food, toys, sport equipment, electronic, tool mold making, aerospace, dental, automotive, armament. So that's all about the industries which is using additive manufacturing. What are the pros and cons? Pros: freedom to design and innovate without penalties. Cons: unexpected pre and post processing requirement, rapid iteration through design permutation, high process cost is the cons. Excellent for mass customization, lack of industry standards is the cons. Pros: elimination of tooling, low speed, not suitable for mass production. It is the cons. Green manufacturing is the pros. Inconsistent material is the cons. Minimal material based is the pros. Limited number of material is the cons. We cannot manufactured all the materials by using additive manufacturing. Energy efficient is the beneficiary. High equipment cost for high-end manufacturing is the disadvantage. Enable personalized manufacturing is the advantage. So these are the advantage and disadvantage. So we can do the rapid prototyping, and in if we are going for mass production, then it is not suitable. Speed is also slow. Benefits: additive manufacturing benefit is the weight reduction. Traditional design versus additive manufacturing optimized design. Source is the saving project. A conventional steel buckle weight 1055 gram. Weight should be reduced on a like for like basis within the saving project. Project partner are Plunkett Associate Crucible Industrial Design EOS 3T PRD Simple Wear Deal Cam University of Extra titanium buckle design with AM weight 70 gram reduction of 55% for an Airbus 380 with all economy seating. This would mean a reduction of 72.5 kg. Over the airplane's lifetime, 3.3 million liter of fuel or approx EUR 2 million could be saved, assuming a saving of 45,000 liter per kg an aeroplane lifetime. Additive manufacturing benefit complexity for free. The complex object you can easily manufacture. If we are going by using conventional manufacturing, then as complexity arises, the cost will be very high. But in additive manufacturing, the cost is constant. Additive manufacturing enables new geometric shape. Additive manufacturing enables the manufacturing of new geometric shapes that are not possible with conventional method. Example, additive manufacturing make it possible to design advanced cooling channels that cool tools component better and therefore reduce cycle time. This source is taken from Ronald Berger. Additive manufacturing for customized medical product. Additive manufacturing holds a large share of the dental crowns and bridges market. Geometry is scanned and processed via CAD and CAM. More than 30 million crowns, copying, and bridges have already been made on additive manufacturing machine over the last 6 years, increasing market share. Experts estimate that more than 10,000 copying are produced every day using additive manufacturing. Faster production: one additive manufacturing machine produces up to 450 crowns per day, while a dental technician can make around 40. What are the implants? Additive manufacturing offer advantage with regard to manufacturing time, geometric fit, and material. Example of a skull implant with modified surface structure, improved fit via AM. Based on 3D scan of the skull, the resulting implant fit perfectly into the skull cap, leads to faster recovery and reduces operation time. Additive manufacturing will replace conventional manufacturing method for customized product. So these are the advantage benefit for customized product. Additive manufacturing will replace conventional manufacturing. Future home manufacturing. The home 3D printer. Suppose you want to make new toothbrush customization, color, handle style and shape. So if you want some new features, then by using this 3D printer you can make. Old toothbrush, this is the old toothbrush, you can recycle it also. Laser scanner to input personalized data, and here new toothbrush is generated. So future is the home manufacturing. In your homes you can manufacture whatever items you want according to your specification, taste, and characteristics. Case study: Rolls Royce Rolls-Royce is considered embarking on the additive manufacture of entire components because of the benefit of faster production and reduced costs that it offers, says Rolls-Royce Neil Mental. At the launch of an engine program, we start to consider for forging, and AM gives us a great opportunity here because conventional method of manufacture can take 40, 50 or even 60 weeks while a component using AM will take 1 month. Likewise, he praised the improved buy to fly ratio on material. Sometimes we machine away 90% of the material to create the final component, but with AM that figure is much reduced. Neil Mentel added that while AM offer distinct advantage, investing in AM machine will require Rolls-Royce to feel confident of their economic viability and that the process will be as robust and reliable as traditional method. Case study of different company Virgin Upper Class Monitor ARM in a technology strategy board funded project for Virgin Atlantic. The arm holding the TV monitor in the airline's upper class seat was redesigned for AM. Let's reduce the arm's weight by 50%, saving 0.5 kilogram for every unit. In terms, saving 45,000 worth of fuel across the 30-year lifetime of the aircraft. You can make an economic case for AM on that one component, said Dr. Chris Tuck, Associate Professor of Additive Manufacturing and 3D Printing Research Group at the University of Nottingham. This source is from Royal Academy of Engineering. Introduction to Reverse Engineering. The primary input for additive manufacturing is CAD file model. Suppose that for a part to be copied, modified, or repaired, CAD was not used in the original design. There is inadequate documentation on the original design. The original CAD model is not sufficient to support modification or manufacturing using modern method. The original supplier is unable or unwilling to provide additional parts. So these are the introduction of reverse engineering. Examining competitive or similar or superior product in great detail by dissecting them or literally taking them apart. So this is the reverse engineering. Suppose you are having any part, then by disassembling all the components, you can study what are the components, how it is running. Technological principle of a device through analysis of its structure, function, and operation. So in here in last slide, the here shown that in additive manufacturing CAD file model is required. In reverse engineering, we have to study what does this do, how does it do that, why would you want to do that. These are the things you have to consider in reverse engineering. Purpose solve dissection and analysis, experience and knowledge for an individual personal database, competitive benchmarking. Reverse engineering process. Digitizing the part. This step uses a reverse engineering device to collect raw geometry of the object. The data is usually in the form of coordinate points of the object relative to the local coordinate system. Building CAD model. This step converts the raw point data obtained from step into a usable format. From physical part, CAD model. After that, prototype part. So from the physical part you have to make the CAD model, then prototype part you have to make. These are the example. General integration of an additive manufacturing. There is a sensor and actuator. What sensor do? Z control for platform movement, XY control for layer plotting, actuator environmental control, temperature, humidity, atmosphere, interlayer control, recoating, head cleaning, etc. Process controller, user interface, licensing system, support generation, process setup, process monitor, internet. What are the materials which is used during the Fabrication by using additive manufacturing, polymer, metal, ceramic, composite. In polymer, ABS polymer, cellulose, nylon, polycarbonate, thermoplastic, polyethylene, polypropylene, polyvinyl chloride. Thermal expansion characteristic is this is the graph which is showing a specific volume on y-axis. Specific volume is the inverse of the density, and x-axis temperature. It is showing with the increase of temperature how the specific volume increase or decrease. For the solid pure metal up to the melting point, the specific volume increase in the linear way, and after melting point specific volume increase in a very rapid way in a vertical direction. Solid alloy up to the solidus stage, if it is alloy, then during the solidification, mm, uh, during the solidification, they their specific volume will increase in also linear way, but its angle will be high. In the case of glass, after glass transition temperature, there will be a different shape. Load displacement characteristics. What are the metal and polymer? Metal characterized by a linear elastic region followed by a non-linear plastic region. Polymer generally brittle at temperature much lower than Tg, but their ductility increases as temperature rises. As the temperature increases to level above Tg, a peak load is reached and a neck begins to form. As the specimen approaches its fracture point, the load rises due to the stretching of molecules. This is the material classification. Laser additive manufacturing of metallic component. Partial melting of the powder, complete melting of powder. If partial melting of powder happens, then laser sintering come into the picture. If complete melting of powder happens, laser melting and laser melting deposition came into the picture. In laser sintering, pre-spreading of powder before laser scanning. Multi-component metal alloy powder, example C2 MMC. In laser melting, pre-spreading of powder before laser scanning. Laser metal deposition, coaxial powder fading with synchronous laser scanning. Pure metal powder, alloy powder, example C2 and in C2 MMC. Metal, pure metal, titanium, tantalum, copper, gold, silver, alloy, titanium base, nickel base, iron base, aluminum base, cobalt base, copper base. Material process consideration and control method. Process of additive manufacturing generally involves a direct interaction of powders with laser beam. The determination of absorption of powder is particularly important to thermal development because it allows one to determine a suitable processing window free of a non-response of powder due to an insufficient laser energy input or a pronounced material evaporation due to an excessive energy input. The absorption is defined as the ratio of absorbed radiation to the incident radiation. The absorption of powder has direct influence on the optical penetration depth of the radiation, which is defined as the depth at which the intensity of radiation inside the material falls to the original value. Owing to the multiple reflection effect, the lambda measured in powder is larger than in bulk material. Surface tension and bettability. The liquid solid betting characteristics are crucial for a successful additive manufacturing process. The betting behavior of a partially melted liquid solid system involves the betting between structural metal and liquid binder as well as betting between the molten system and the solidified pre-processed layer. For the completely melted LM-LMD system, the second kind of betting behavior prevails. The betting of solid by a liquid is related to the surface tension of solid liquid, solid vapor, solid liquid vapor interfaces. Bettability can be defined by contact angle. The liquid bets the solid as cos theta is greater than 1. A spreading coefficient has been defined in literature to describe the betting behavior, and normally a larger positive yes favor spreading of the liquid. Next property is the viscosity. Beside the favorable bettability, it is required that The viscosity of melt is low enough such that it successfully spread on previously processed layer, and in the case of liquid solids around the solid structural particle. For ALS system consisting of a solid liquid mixture, the viscosity of molten material mu is expressed as, where mu naught is the base viscosity that include temperature term. Phi L is the volume fraction of liquid phase. Phi M is the critical volume fraction of solid, above which the mixture has essentially infinite viscosity. Ceramic additive manufacturing technology has been successfully demonstrated its advantage in producing ceramic parts through both direct and indirect method. Indirect method, these processes typically create a ceramic green body with a high content of organic or inorganic binder. Then binder burnout and densification of the green body are conducted in conventional sintering steps. Direct method, direct fabrication of ceramic part using additive manufacturing process is much more challenging due to the high melting temperature of ceramics such as Al2O3, silicon dioxide, and also the large thermal gradient, thermal stresses, and residual stresses associated with melting in the laser-based additive manufacturing process. Composite are engineered or naturally occurring material made from two or more constituent material with significantly different physical or chemical property that remain separate and distinct at microscopic or microscopic scale within the finished structure, but exhibit properties that cannot be achieved by any of the material acting alone. The material in a composite can be mixed uniformly, resulting in a homogeneous compound, uniform composite, or non-uniform resulting in an inhomogeneous compound. Example, functionally graded material in which the composite varies gradually over volume, leading to corresponding changes in the property of the composite material. Uniform composite and composite functionally graded material. Composite, these are all about the two composite. Additive manufacturing unique capability, shape complexity. It is possible to build virtually any shape. Hierarchical complexity, feature can be designed with shape complexity across multiple size scale. Various types of nano microstructure can be achieved by careful control of the process parameter. Laser power scan rate for a particular material and can vary from point to point within the structure. The ability to simultaneously control a part's nano, microstructure, mesostructure, and microstructure simply by changing process parameter and CAD data is capability of additive manufacturing, which is unparalleled using conventional manufacturing. Additive manufacturing unique capability, functional complexity, functional devices can be produced in one build. Material complexity, material can be processed one point or one layer at a time as a single material or as a combination of material. When building parts in an additive manner, one always has access to the inside of the part. Component can be inserted and it is possible to fabricate operational mechanism in some AM process. Pulley driven snack like robot source. Source is the Gibson. This is the pulley driven snack like robot. Additive manufacturing unique capability. The concept of functionally graded material or heterogeneous material has received considerable attention. However, manufacturing useful part from this material often has been problematic. Example, turbine blade for a jet engine. The outside of the blade must be resistant to high temperature and very stiff to prevent elongation. The blade root must be ductile and has high fatigue life. Blade interior must have high heat conductivity so that blade can be cooled. A part with complex shape that require different material property in different region. No single material is ideal for this range of property. A significant issue hindering the adoption of additive manufacturing material complexity is the lack of design and CAD tools that enable representation and reasoning with multiple parts. Process planning in layered manufacturing. Data transfer, one process planning task, pre-processing of model for manufacturing. Data transfer to material process task, build model using supplied build material. Reverse engineering, generate a CAD model for the manufacture of a part. Process planning in layered manufacturing. There are four main planning tasks: orientation, optimization, support design, slicing, tool path, scanning, path planning. Simple STL file, advantage and disadvantage. This is the STL file. What are the advantages of STL file? Provide a simple method of representing 3D CAD data. A de facto standard has been used by most CAD system and RP system. It can provide small and accurate files for data transfer for certain shape. Disadvantage: the STL file is many times larger than the original CAD data file. The geometry flaws exist in the STL file. The subsequent slicing of larger STL file can take many hours. STL file problem: gaps, crack, holes, punctures that is missing facet, degenerate facet where all its edges are collinear, overlapping facet, non-manifold topology condition. These are the some STL file problem. Valid versus invalid tessellated model. These are the some STL file repair. If there is the problem in the STL file. Layer manufacturing process: powder material, sintering process, printing or joining process, liquid material extrusion process, liquid polymerization or stereolithographic process, solid material lamination process. Stereolithography. Facts about stereolithography: part build time in steel. This is the numerical problem. How layer by layer addition take place in stereolithography. That's all the end of the today lecture. Please, dear student, if you did not subscribe my channel, please subscribe so that you can get more useful video. I am going to stop my lecture.